This section covers the fundamental concept of regression coefficients. A regression coefficient measures the expected change in the dependent variable for a one-unit change in the independent variable, while holding all other variables constant. The most basic form of regression is the simple linear model. In this equation, y is the outcome we're trying to predict, and x is our predictor variable. Let's break down the components of this equation. Regression analysis is a vital statistical tool with wide-ranging applications. It's used for statistical inference, quantifying policy change effects, testing economic theories, understanding relationships between economic indicators, and forecasting future trends. Simple linear regression models the relationship between a predictor variable x and an outcome variable y using a straight line. Let's visualize this equation on a coordinate system, with x as our predictor variable and y as our outcome variable. In this equation, beta 0 represents the intercept, which is the value of y when x equals 0. Beta 1 represents the slope, which is the change in y for each one-unit increase in x. In regression analysis, we fit a line through scattered data points to find the relationship between x and y. Here we can see a geometrical representation of the regression model where the vertical distances between data points and the line represent estimation errors. Let's break down the regression equation. Y is our outcome variable. Beta 0 is the y-intercept, the value of y when x equals 0. Beta 1 is the slope, representing the change in y for each unit increase in x. And x is our predictor variable. Here's another way to visualize regression, showing the line of best fit through data points with a confidence band around it. This diagram clearly shows how the line intersects the y-axis at beta 0 and how the slope beta 1 determines the steepness of the line. To summarize, simple linear regression fits a straight line to our data. The intercept beta 0 represents the y value when x equals 0. The slope beta 1 represents how much y changes when x increases by 1 unit. Unlike simple regression, multiple regression includes several predictors in a single model. The equation expands to include multiple terms, y equals b(x1) plus b2x2 and so on, plus a constant term a. Each coefficient represents the partial effect of that predictor on the outcome, holding all other predictors constant. Let's examine a model with 3 predictors: age, BMI, and smoking status. Each has a different effect on our outcome. This visualization demonstrates how each predictor has a linear relationship with the dependent variable when other variables are held constant. Added variable plots, also known as partial regression plots, help visualize the relationship between each predictor and the outcome, after accounting for all other variables. When interpreting partial effects, it's crucial to verify that model assumptions are satisfied. These diagnostic plots help assess linearity, homogeneity of variance, and other important assumptions. To summarize the concept of partial effects, each coefficient isolates the effect of one variable while holding others constant. These relationships can be visualized through partial regression plots, and we must always verify that regression assumptions are satisfied. Logistic regression is different from linear regression because it predicts probabilities rather than continuous values. In logistic regression, coefficients are measured in log odds units. The logit function transforms probabilities, which are bounded between 0 and 1, into log odds, which can range from -infinity to +infinity. To make interpretation easier, we exponentiate the coefficients to convert them from log odds to odds ratios. An odds ratio tells us how much the odds of the outcome change for a one-unit increase in the predictor. Let's look at a concrete example. If we have an age coefficient of 0.049, we exponentiate it to get an odds ratio of 1.05. This means that each additional year of age multiplies the odds of disease by 1.05, or increases the odds by 5%. For a negative coefficient, like a treatment coefficient of -0.693, the odds ratio is 0.5. This means the treatment reduces the odds of complication by half, or by 50%. Let's look at a real-world example about smoking and mortality to see how we interpret logistic regression coefficients in practice. This statistical output shows a logistic regression where smoking is the predictor and mortality is the outcome. The coefficient for smoking is 0.517 in log odds units. When we exponentiate this coefficient, we get an odds ratio of 1.67. This means that the odds of death for smokers are 1.67 times higher than for non-smokers, controlling for other factors in the model. The statistical output also provides a 95% confidence interval for this odds ratio, ranging from 1.27 to 2.19. This means we're 95% confident that the true odds ratio falls within this range. To summarize, logistic regression coefficients are in log odds units. We exponentiate them to get odds ratios for easier interpretation. An odds ratio greater than 1 indicates increased odds, while an odds ratio less than 1 indicates decreased odds. For percentage change, subtract 1 from the odds ratio and multiply by 100. Statistical significance and confidence intervals are essential concepts for interpreting regression coefficients. P-values measure the strength of evidence against the null hypothesis that a regression coefficient equals 0. A p-value represents the probability of observing a result as extreme as or more extreme than our sample result if the null hypothesis were true. Typically, a p-value less than 0.05 indicates statistical significance, suggesting we have evidence the coefficient is different from 0. Confidence intervals provide a range of plausible values for the true regression coefficient. A confidence interval is calculated using the estimated coefficient plus or minus a critical value times the standard error. The critical value depends on the desired confidence level, typically 95%, and the sample size. A confidence interval helps visualize statistical significance. When the interval excludes 0, we have a statistically significant result. Let's look at a regression example showing the relationship between car speed and stopping distance. The regression coefficient is 3.932 with a 95% confidence interval from 3.124 to 4.740 and a p-value less than 0.001. We can interpret this as, for each 1 mile per hour increase in speed, the stopping distance increases by approximately 3.9 feet. Since the confidence interval doesn't include 0 and the p-value is less than 0.05, this effect is statistically significant. Here's another example comparing the effect of different tensions on wool breaks for two types of wool. The regression coefficient for wool B compared to wool A is negative 5.78, with a confidence interval from negative 7.40 to negative 4.16 and a highly significant p-value. This means wool B has significantly fewer breaks than wool A, with an estimated 5.78 fewer breaks on average. Since the confidence interval is entirely below 0, we're confident this difference is real and not due to chance. To summarize, p-values below 0.05 indicate statistically significant results. Confidence intervals show the precision of our estimates. Remember that statistical significance doesn't always mean practical importance, and confidence intervals that exclude 0 indicate statistically significant coefficients. Let's explore how regression models help predict hospital readmissions in real-world healthcare settings. Many hospitals track readmission rates as a key quality metric, especially for conditions like diabetes. Our logistic regression model predicts hospital readmissions based on two key factors: length of stay and discharge disposition. The model coefficients reveal the direction and magnitude of each factor's influence. The negative coefficient for length of stay suggests a protective effect, while the positive coefficient for nursing facility discharge indicates increased risk. When explaining regression results to healthcare stakeholders, we translate statistical coefficients into plain language. For the length of stay coefficient of negative 0.15, we can say that each additional day a patient stays in the hospital decreases their odds of readmission by 14%. For the discharge disposition coefficient of positive 0.65, we explain that patients discharged to nursing facilities have 92% higher odds of readmission compared to those discharged home. These regression insights can be applied to clinical decision support systems, helping healthcare providers identify high-risk patients and determine appropriate transitions of care. When interpreting regression models, we must consider the combined effects of multiple factors. Let's examine how different combinations impact readmission risk. For a patient with a 2-day hospital stay who is discharged home, the model predicts only 18% probability of readmission. However, for a patient with a 1-day stay who is discharged to a nursing facility, the probability jumps to 33%, demonstrating the strong impact of discharge destination. Translating regression coefficients into actionable insights helps healthcare teams implement targeted interventions. To conclude, remember that regression coefficients must be transformed into probabilities for meaningful risk prediction in clinical settings. When communicating with healthcare stakeholders, focus on the practical interpretation of coefficients rather than the statistical details. This makes complex regression models accessible and actionable for clinical teams.